So thank you so much for the invitation, and it is fun that I get to give talks in places I wouldn't regularly get to give talks. So yeah, I'm happy to virtually be visiting you. So yeah, I'll talk about joint work with Megumi Harada. And I will spend a long time motivating Newton-Okounkov bodies. And then I will tell you about the wall crossing that Megumi and I introduced. So first, I'll start way back just because I really want to motivate Newton-Okounkov bodies. So I'll start with the Newton polytope. So the Newton polytope of a polynomial or a Laurent polynomial is just the convex hull of the exponent vectors that for which the coefficients are non-zero. And so, for example, here we have that the Newton polytope of this polynomial is just, okay, so this is the exponent 2, 0, so we get this point, then 0, then, sorry, I didn't fix this typo, 0, 1 corresponds to this one, and 0, 0 corresponds to that one, and then we get this triangle. So the Bernstein-Khovansky-Kushnirenko theorem relates the geometry of this polytope with some geometric information of this polynomial. So more precisely, if you pick a finite list of exponent vectors that you care the most about, and you construct a vector space, which is all the polynomials that have those exponent vectors. Okay, so in other ways, you're allowed to change the 3, this 1, and this -1. They can be any number you'd like, but you do want to have exactly those 3 monomials. So for a generic choice of elements in here, so if you pick n generic polynomials inside this vector space, so you let the variables, the coefficients be random, then the number of solutions to the system of equations in C star to the n is n factorial times the volume of the Newton polytope. And so here, just as a sanity check, the volume of this polytope is 2, is 1, sorry, and it lives in R2, so we would hope that if we look at the number of solutions to 2 of these polynomials with random chosen coefficients, we should get 2 solutions, and I mean, that seems right. So now this theorem can be restated as giving a formula for toric varieties. So if you start with a polytope in Rn, you can construct a projective toric variety, and then you have this relationship that the n factorial times the volume of your polytope is equal to the degree of your projective toric variety. So this is a result. Well, I like polytopes a lot, and I like toric varieties, and I like that they interact, and this is a very beautiful result. And like both of these results have consequences in combinatorics, for example. So like you can actually, not only can you use polytopes to find volumes of it, to find degrees of varieties or number of solutions, but you can also do it the other way around. So for some families of generalized permutahedra, if you want to find their volume, you can actually write a system of solutions and argue and count how many solutions it has. So this is a result that like the theory of Newton-Okounkov bodies, it generalizes. So if you start with an irreducible projective variety over C, so I want a far more generality. Most varieties are not toric varieties, so I want to start with a more general variety, and I denote throughout the talk A. It's going to be its homogeneous coordinate ring. Then the theory or Newton-Okounkov bodies which were introduced by Okounkov, but actually like the theory, the foundations of the theory were set up by Lazarfeld, Mustata, and Kaveh-Manon. They roughly, so I'll give more details, but from a bird's eye point of view, you start with a valuation on this ring, and you construct a convex body from that valuation. And then the key thing is that the degree of your variety is then going to be n factorial times the volume of your polytope. So other than like being flipped, we have a far extension of this relation between toric varieties and polytopes, and we extend it to more general settings. Okay. So before I give you details on Newton-Okounkov bodies, well, what have they been used for? So David Anderson, proved that when your Newton-Okounkov body, your Newton-Okounkov body does not have to be a polytope. It's just a convex body. But when it is a polytope, and it's a lattice polytope, and the dimension of your polytope is equal to the dimension of your variety, then you can find a toric degeneration of your original variety to the toric variety of this polytope. So a flat family. And Megumi Harada and Kaveh proved that when you have a smooth variety, then given that you have this degeneration, you can ask is there a symplectic story that you can tell here? And they told a symplectic story. They said that when you have a smooth variety, then you can find a full dimensional Hamiltonian torus action whose moment map image is this Newton-Okounkov body. And well, I will touch a little bit into this, but there have been applications to cluster varieties. So one of my favorite is by Connie Rich and Lauren Williams, who use Newton-Okounkov bodies to talk about they use cluster varieties to construct Newton-Okounkov bodies for Grassmannians. And they use this to give a mirror symmetry framework for Grassmannians for Gr, Kn, using positons, which is very beautiful work. But I'll touch more concretely into this because even in the work with Megumi, we encountered a connection to cluster varieties. But now let me give you the concrete construction of a Newton-Okounkov body. That it's not the key is understanding evaluation. So once evaluation is out of the way, defining a Newton-Okounkov body is not too hard. So you're gonna equip z to the n with a total order, and evaluation is gonna be a map from your coordinate ring without the origin to z to the n, such that you want these three properties. So you can think about it being like the degree of a polynomial, right? Because let me think, I forget, sometimes, okay, so the degree can mean the highest term or the lowest term. And here, I want the lowest term. So it's the degree of the lowest term in your polynomial, right? Because if you add two polynomials, well, the degree of the lowest term could stay the same, or there could be cancellations, but then the degree increases. The degree of the product of two polynomials is the sum of the degrees, and constants have degrees here. So this is a vast generalization of the degree of a polynomial. And valuations in general provide tools to generate coordinate rings of varieties into simpler subalgebras. So the best case scenario is when you can have a polynomial ring generated by monomials. So here we have similar to the example I was saying before, but a more general, like a multi, not like the degree as in maybe the multi-degree. So here, if you have any polynomial, you can consider evaluation that it's the minimum of the exponent vectors. So it goes really to c to the n, or to c to the, to this n. And it's the minimum among the exponent vectors where the coefficients are non-zero. And this is evaluation. And I wanna start motivating some of the objects we encountered. So an important one is the image of the evaluation. And the image of evaluation for this valuation It's just gonna consist of these lattice points. Okay. So in general, the image of evaluation is gonna be, yeah, a semi-group in Z to the N. So another example that, and this one is going to be a bit more mysterious, so you'll have to trust me that it is evaluation, and I'll tell you why. But for now, maybe it's unclear why it is. But if you start with this hypersurface, and here I'm just taking this matrix from nowhere, but if you consider this matrix, you can define evaluation from the coordinate ring to Z2 that it takes any, oh, now Y got deleted. I wonder if I can write it down. I'm not sure why. But if you take any element of your coordinate ring and you just, so I actually want to present it, right? So I'm presenting this coordinate ring as the quotient of C of X, Y, Z by the ideal generated by this. Let's see if I can write my Y. So you take any element of the coordinate ring and you map it to the minimum of the product of this matrix by the exponents. Okay? So you take the exponent vector, you write it in a vector, and you multiply, and you consider all the minimum of these products where the coefficients are non-zero. And a fact is like, yes, that is number one, well defined, and number two, evaluation. But given that you believe those two facts, we have that the image of the evaluation is going to be now this lattice points that we have over here, and it's the same.
Sorry.
Oh yes.
So the minimum, so you order Z2 lexicographically or any other?
No, I did. Yeah, you're right. I ordered it lexicographically. So I fixed a total order, but it's always going to be the lexicographic order for this talk.
Okay, thanks.
Good. So then once we have this relation, the image of the evaluation is the semigroup generated by the columns of this matrix that I drew over here. So now this semigroup is skipping this row, but that's what the image is. And in general, the image of evaluation is a semigroup. Is it finitely generated? Not always. I mean, the Newton-Okounkov body is not always a polytope, so, and that's very much related to this image not always being finitely generated. So for the Newton-Okounkov body, now that we understand valuations, what we have is simply you just take the image of your valuation, you take the cone over that image, so you just here you just span the cone, you take the cone spanned by the elements of your semigroup, and you take the closure, and that's like, we need the closure because semigroups aren't always closed and crazy things can happen, and maybe you don't see that here, but you do need the closure, and you intersect with the hyperplane where x1 is 1. So here we have the example. This is the Newton-Okounkov body for the example we were looking at before. So as I was hinting at before, this Newton-Okounkov body is a polytope if the image of your valuation is finitely generated. So there's like here, remember we started saying, oh, well, Newton-Okounkov bodies have this very nice property that the degree of your variety is equal to the volume of your body. But like in general, of course, that can be very hard to relate. And well, more importantly, one of a very important application is the one that I mentioned from Anderson, which is that like if you have a polytope, you can have a toric degeneration. So there's like having good valuations is very important, and like one of the first properties that I would say is important for valuations is for the image to be finitely generated. So like coming up with methods to give families of valuations over varieties or a fixed variety even that are finite, that whose image is finitely generated it's an important program in general. So before, well, yeah, like Humors and Chris, they carried out this program. They gave big families of valuations with finitely generated images, and they use tropical geometry to do this. So yeah, this is they use tropical geometry to construct valuations whose Newton-Okounkov bodies are polytopes. And the key, okay, so tropical geometry is a very deep theory, and I will warn you that yes, I'm just gonna use the baby version of it. So what is a baby version of tropical geometry? Well, if you start with an ideal, you can define the tropicalization of your ideal as the points, the points in Q to the n, such that the initial ideal contains no monomials. So, and in case you're not very familiar with initial ideals, I'll say in words that the initial, okay, so this initial ideal is the ideal generated by the initial forms with respect to W of all polynomials in I. And the initial form of a polynomial is just, okay, so you have your polynomial, it has a bunch of exponents. So for each exponent corresponding to a non-zero term, you take the product of that, the dot product of that with W, and you look at the minimum and all the terms that attain those minimums are the elements in your are the terms that you add up to get the initial form of your polynomial. And actually, there's a way to describe it in terms of the Newton polytope, because that was a bit maybe hard to follow, that if you have a polynomial and you consider its Newton polytope, then W, you pick a vector direction, and that gives you a face, and you just look at all the terms corresponding that whose exponent vectors lie on that face. But anyways, so here, initial ideals are great, like they provide, again, flat degenerations of algebras to simpler algebras, but here when you look at tropicalization, there's this nice thing that, well, suppose you care about toric degenerations, which I do, then like you actually want to consider initial ideals that contain no monomials, because you want to end up with a binomial ideal. And tropicalization provides a tool for that, as I think we will see. But if not, I'll tell you in a minute. Okay, so this is the tropicalization. It's just, for now, it's a set that encodes all the different initial ideals that your ideal can have, as long as none of those initial ideals contain a monomial. But now I'm going to impose an extra structure. So the extra structure is that of a fan. So I'm going to define cones, the cones of the tropicalization of an ideal, to be the points in the tropicalization that give you the same initial ideal. And you take the closure of that. Okay, so briefly, one example that we have here, and this is the example we had before. But so the tropicalization of this ideal is gonna consist of, well, so it consists of, you're gonna have a bunch of cones. This is one of the cones. It's the cone spanned by the ray 0, 1, 0, and then you have this linearity space, this vector space. So it's the sum of a cone with an honest cone with a vector space. Then you have this other cone, and then you have that third cone. Those are your maximal dimensional cones. And then it's a fan. So for example, just the cone spanned by, or yeah, the line going through 1, 1, 1. This is 1, 1, 1. Will also be one of the faces of your tropicalization. And for the maximal ideals, for the maximal cones, for example, this one, all of the points inside here or in the interior of this cone will give you, will give you the same initial ideal. Will give you this initial ideal. And similarly, for this one, you will get that ideal, and for the last one, you will get this ideal. And in that sense, this one has a star because it's very special. Why is that? Well, I'll define it. Yeah. Notice that this, or which one is easy to see? This one is easy to see. This one is not a prime cone, a prime ideal. So I don't like it. And if you're really good at recognizing prime ideals, you'll see this one is also not prime. So this one is special because this ideal is prime. And Chris and Kumers introduced this, noted that whenever they have a prime cone in the tropicalization, they're able to construct these valuations that we're seeking. So let's introduce that as a definition. That a cone in the tropicalization is prime if the initial ideal is prime for one or any, it doesn't matter because of the definition of the cones, elements in the interior. And one thing that I want to say now is that, well, whenever you have a maximal cone in your tropicalization that is prime, you'll have that you have a binomial ideal, and because of that, it's going to be the ideal of a toric variety. So hidden in all this, you'll also have a toric degeneration. So it's just being very naive. It makes sense that one could relate these two stories because Newton-Okounkov bodies give toric degenerations, and prime ideals in tropicalization give you also toric degenerations, and this will be a way to relate the two stories. So Chris and Kumers tell us that if you start with a prime cone of the tropicalization, then you can construct, or for each prime cone of the tropicalization, you can construct a valuation, and the method is the following. So you pick. Let's suppose that your cone has dimension R, and you're going to pick R elements in your cone that are linearly independent. And then you construct a matrix that has the rows, those vectors you just picked. And then you construct a valuation as follows. So, I guess I'm not writing it here, but we will see it in an example. So you construct a valuation that satisfies the following, that the Newton-Okounkov body is going to be the convex whole of the columns of your matrix. Now, how do you construct a valuation? That is literally the example we had before. That let me just go back for a second. It's you construct them in this form, basically. And the key is going to be that those are going to end up being valuations, and they're going to be well defined. So you replace this M over here with the M that I told you how to construct. Okay, so we are here. So, well, as long as you know how to compute the tropicalization of an ideal presenting the coordinate ring of your favorite variety, you can, and you need to be able to really compute it. But as long as you can do that, then you can construct valuations whose images are finitely generated semigroups and whose Newton-Okounkov bodies are polytopes.
Sorry, can I ask you a question? So
yes.
This means this Newton-Okounkov body is not unique for the cone C.
Yeah, that's a good question. So yeah, there was a choice here, right? I made a choice there, but that choice, yes. So technically the polytope can change if I change the choice that I make there, but you can relate all the different ones that you would get within one cone. they would be related by a linear map. So a piecewise linear map that is like actually very simple to describe. And they're all gonna have the same volume, and so yeah, they're gonna be combinatorially the same. So even though it looks like this is an important or a big choice, there is not. It's like not that important.
Okay, thanks.
Mm-hmm. Okay, so let's look at an example and let's talk about the Grassmannian Gr 2-4, which, and I'll consider it Splucker embedding, so I'm gonna consider this ideal, the Splucker ideal. And then the tropicalization is gonna be the product of this fan, and so there's nothing here, right? These things are empty. So of this fan with a 4-dimensional vector space. And a nice feature about the Grassmannian Gr 2M is that all of the cones in its tropicalization are prime. And so this is like perfect to apply the machinery developed by Chris and Kumers. So if you have 2 prime cones of maximal dimension, just because they'll give us the Newton-Okounkov bodies containing the most information, then you can construct valuations, nu C1, nu C2, and their respective Newton-Okounkov bodies, and you're gonna have respective semigroups nu C1 and nu C2. Okay, so here this just means I'm applying the machinery that I described before by Chris and Kumers. Now, one description, this tropicalization was described in a lot of detail by Speyer and Sternfels, and they describe it in terms of phylogenetic trees, but I'll tell you the dual story, which is via triangulations of polygons. So the maximal cones in the tropicalization of the Splucker ideal I2M correspond to triangulations of a labeled M-gon. So you choose a labeling of the vertices. You cannot change it anymore. Oh, wait, no, sorry. You do change it. No, yeah, that was wrong. No, so triangulations of labeled M-gons. So you get to change the labels, okay? So this corresponds to one of the maximal cones. You have this, you take a square for Gr 2-4, you triangulate it and you label the vertices. That will give you one maximal cone. And this will give you another cone, another maximal cone, which again, you take a square and you triangulate it and you label the vertices. So if you take any M-gon and triangulate it and then label the vertices however you want, that will correspond to a maximal cone, and all maximal cones can be described in that way. Now, adjacency in this description is very nice, that you have that 2 maximal cones in the tropicalization are adjacent if you can relate them by a flip. And the labels of the vertices are important for that flip, right? So if you flip this diagonal into that diagonal, you get a different cone, and these 2 cones are going to be adjacent to each other. Okay, so what Megumi and I were interested in is, before I go to that, is just to, like, on this end we have a Newton-Okounkov body, on this end we have another Newton-Okounkov body, and we wanted to give a combinatorial rule that describes the relationship between those 2 polytopes. In other words, we wanted to give a piecewise linear map from the Newton-Okounkov body of this corresponding to this cone to the Newton-Okounkov body corresponding to that cone. And so here, if we denote this is going to be the map. So if we this polytope lives in R to the 5, in R to the number of Splucker coordinates, each of them do. And wait, actually, no, not, yeah, there's 6 Splucker coordinates. It lives this, like, okay, so it lives in the Plucker coordinates that correspond to edges of the polygon, right? So this is 1, 2, 1, 3, 1, 4, 2, 3, 2, 4. So those are the coordinates, labeling the R in which the polytope corresponding to this cone lives. And similarly for this one, get 1, 2, 1, 4, 2, 3, 2, 4, and 3, 4. And so the piecewise linear map that maps this polytope to that polytope it's basically the identity on all the coordinates that they share. So Z12 stays the same, Z14 stays the same, C23 stays the same, and C34 stay the same because they appeared here. And then C24 changes, and it's gonna be the tropicalization of this rational function. And by tropicalization, so there's two notions, well, I mean, they're all related, but in this talk, there's two notions of tropicalization, and the tropicalization of this rational function is just, you change it into a piecewise linear function, okay? So pluses become minimum, and products become sums, and divisions become subtractions. And this piecewise linear map was introduced by Nohara Ueda, that they encountered it. So they were very interested in introducing toric degenerations for Grassmannians. And they constructed toric degenerations for Grassmannians 2M using integrable systems, and they related, they gave piecewise linear map between them, and this is the piecewise linear map by Nohara and Ueda. So now I can tell you about the geometric wall crossing for Newton-Okounkov bodies that Megumi and I gave. So again, to revisit, we're gonna start at the level, or to emphasize that this is for in a very general setting. If you have a projective variety X and you take A, it's coordinate ring, but I want to present it. I'm gonna pick a presentation. Why? Because I need to take tropicalization. So if you take two prime cones of the tropicalization, such that they're both of maximal dimension, and they share a facet that I'm gonna call C, so they're adjacent to each other, well, then the first part of our theorem is the following, that you have a projection. And I guess this is not actually our theorem. This is not too hard to see, that if you make the right choices. So here, of course, I'm being a little bit, I'm hiding the machinery in this notation a little bit. But remember that, I needed to look at some matrices. So each of these prime cones, I need to consider matrices for them, but I can make choices for the matrices that are compatible with each other, mainly via the C. And if you make those choices correctly, then it's not too hard to see that the Newton-Okounkov bodies, they both project to the same Newton-Okounkov body, the Newton-Okounkov body for the valuation associated to this C. And this is just a very natural projection. So what Megumi and I proved is first, and this was the harder part of the result, is that if you look at the fibers under these maps, then they're intervals of the same length. Okay. So in this, here is the picture of what's going on. So let's suppose that this is a Newton-Okounkov polytope for the valuation corresponding to the cone in the intersection. And I pick a point in the Newton-Okounkov polytope. Then the fibers are these two intervals, and they're gonna be of the same length. So the fact that they're intervals, again, is clear from this whole setup, but the fact that they're the same length is surprising. But now, once you have this result, we are able to obtain two piecewise linear maps, because here, if you look at the picture, our goal is to give a map from here to there, a piecewise linear map from here to there. And what you can do, if you have like a bunch of columns next to each other that form this shape, then you can basically like shift your columns up and down so that this shape becomes that shape, right? So you in this particular case, you can leave this whole piece fixed and then start shifting columns on this triangle up so that it becomes this shape. So that's one of the piecewise linear functions we have. So we obtain two piecewise linear maps, the shift and the flip. And the shift is literally what I just told you. And the flip is just, well, if you take this polytope and you flip it, you still have a polytope that satisfies these properties, right? That it projects to the same as this other one, and the fibers are intervals of the same length. So if you flip this one upside down, nothing will change. So you could, the second piecewise linear map is flip that top polytope and then apply this shifting. So we obtain two piecewise linear maps such that this diagram commutes. So some remarks about our theorem, and it's that, well, this paper started, or this project started at the Fields program on roughly combinatorial algebraic geometry. I think it was 2017. And then we were talking about a lot of things, and then Nathan Nilton and Grassmannian were working on geometric. They were working on complexity 1T varieties. So they were like, this is a really nice paper, because if you think about what I'm telling you, like, as soon as I was constructing my polytopes, like when I was telling you the result with Megumi, the top part was like, I need a presentation for the coordinate ring of my variety. So I need an embedding. So a natural question is like, can I embed my variety so that the resulting tropicalization has a prime cone? Because if it has a prime cone, I can have a toric degeneration. Or more excitingly, all the maximal cones on the tropicalization are prime. And so Nathan Nilton and Grassmannian, they address that question for complexity 1T varieties. So yes, you can, if you have a complexity 1T variety, you can find an embedding such that the tropicalization has all cones prime. And as they were doing that, they realized that the geometric wall crossing that I'm giving you, I'm calling this one geometric, can be derived from the theory of complexity 1T varieties. And moreover, so these two things you can read about on the appendix to the paper by Megumi and me. And Nathan also gave a very nice interpretation of the geometric wall crossing that I'm describing here as a generalization of the combinatorial mutation of Akhtar, Coates, Galkin, and Hasprin. I should have asked how to say your last name. I'm so sorry. But anyways, I tried. And then on the other hand, we also gave an algebraic wall crossing. So we gave a bijection. It's not a semigroup map. It's just a bijection between this semigroup and that semigroup. And then again, this, like, if you said things right, having this projection, like the maps that go down are just projections, and projections of semigroups. So we give a bijection of this valuation to that valuation that makes this diagram commute. And for Gr to M, we notice, and so there's different levels to notice this, and maybe I should take you back to the example after I give this remark. But for Gr to M, the flip map, the geometric flip map, arises from the cluster algebra structure of the Grassmannian. And I'll show you what I mean well, what Megumi and I meant in our paper. But this like cluster algebras again is another theory that is now very deep, despite it being fairly recent. And there's different ways to say how this arises from the cluster algebra structure. And Lara Bossinger, Fatime Mohammadi, Natferda Nahera Chavez, they gave a much deeper connection. So this interacts very nicely. Even the algebraic wall crossing interacts very nicely with the cluster algebra structure of the Grassmannian. But just to emphasize one thing in this example we have over here, if you look at it, if you're familiar with cluster algebras, this should speak to you, right? Because the cluster mutation is what goes inside here without the tropicalization. You take the Fluker to 4 and it's equal to this, but more importantly, this is a cluster mutation. Okay. So let me see. Okay. So I need to change slides because I wasn't sure when I was going to finish, but let me change. So to finish, I just want to give you an idea of the proof of the fibers statement of the theorem. So let me see. Yeah, of this part of the theorem. It looks a little bit different. So sorry about that. But I just wanna give you an idea of the proof. So since the two cones that we're looking at are prime and maximal dimensional, then as I told you before, this initial ideal is toric. And the variety for this ideal is the toric variety of this Newton-Okounkov body. And this is known basically, okay, so why is this true? This is true because this Newton-Okounkov polytope is the convex hull of the columns of that matrix. And so tropical geometers know this, that whenever you have a toric idea, like whenever you have a prime and maximal dimensional ideal, the initial ideal corresponding to that cone is going to be the toric variety of the polytope constructed from the columns of the matrix. But so let xi be the, like here, let me introduce some notation. Xi is the toric variety of each of the cones. And y is the variety of this ideal. And this is no longer a toric variety, but it's a variety corresponding to an ideal. So then you can find flat families over A1 with generic fibers isomorphic to Y and special fibers isomorphic to each of these toric varieties. Okay, so I'm going to have two flat families. And this follows from the theory of well, I'll call it Grobner degenerations, even though Grobner degenerations degenerate to monomial ideals, but it's the same. When you have an initial ideal, you always have flat families. Now here, this interacts nicely with a torus section. So these are toric varieties, so they have a torus section. And so each of them have torus actions, and Y is not exactly a toric variety, but there is a codimension 1 torus. So this is what torus is this? This is the subtorus of the torus that acts on each of the xi's. So it's like the torus that both of the xi's have in common. And the toric variety of a fiber of the, so remember, so I'm gonna like, so if I remember, I want to show that the fibers have the same length. So if I look at a fiber in one of these Newton-Okounkov bodies and I take the toric variety of that fiber, okay, well, it's just an interval, but this is the GIT quotient of the toric variety of this polytope by T at that point. Now this torus action on Y extends to the flat families that I mentioned above. Okay, so in some sense, okay, so the toric families sorry, this torus action extends to these flat families. And by taking the GIT quotient of each of those families by T at the point I'm taking the fiber, we're able to get two flat families. So this is variation of GIT. And the first one, or they both have the generic fiber of this GIT quotient, and each of them has these special fibers. Okay. So remember, this is a toric variety of the fiber. That's what we discussed at step 3, for each of the fibers. Now, flat families preserve degrees. So we have this very beautiful sequence of equalities, that the length of the first fiber is equal to the degree of this quotient because of toric varieties, right? This is the toric variety of this fiber. And then flat families preserve degrees. So we have this flat family relating this to degrees. We have the other flat family preserving this to degrees. And then again, you have this equality because one is the toric variety of the other. And so you have that the two fibers actually have the same length. But yeah, I think that is all I have to say today. So thank you so much.